In this video, I will look at using RETScreen to determine the feasibility of a solar air heating collector for an industrial building. This analysis can also be found in the RETScreen case studies and templates. If you search for Dorval, that is the location of this project. It's just outside of Montreal, Quebec, Canada. It's where the Montreal airport is located. So searching for Dorval will find that. The situation of this building is that it's a large manufacturing facility with 116,000 square meters of floor space, and it's a 12-meter high building. It operates 24 hours a day year-round. For good air quality, there's a large fresh air requirement of 1 million cubic meters per hour. Heating is required for this air from mid-September through mid-May. Natural gas is currently used, and that is very expensive. So they are looking to see if a solar air heating system would be feasible. We have two exterior walls on which the solar collector could be affixed. One faces southeast, the other southwest. Together, they could accommodate a collector of 8,826 square meters. We want to evaluate the benefits of not just solar air heating, but also reduced heat losses from the walls and ceilings due to the solar air heating system, and destratification, that is, a reduction in the accumulation of hot air near the ceiling where it is not useful. I've set the location already to the Montreal International Airport, which is very close to where this building is located. On the facility page, I'll need to select for the facility type individual measure and for the type solar air heater. On the energy page, I've already selected natural gas as a fuel and put in the price, and electricity is also available for this analysis should we need it for the fans. I'll need a conventional heating system in the base case and in the proposed case as well for that portion of the heat requirement that cannot be met by the solar air heating system. This is going to consume natural gas. It will have an efficiency over the entire season of use of 75% in both the base case and the proposed case. Next, I will add a solar air heater from step 4, Optimize Supply. For the facility type, I'll have to choose industrial here. In a commercial, institutional, or residential building, a constant flow rate is maintained through the solar collector. And if the temperature of the air exiting the collector is too low, heat is added, for example, by a gas-fired heater. In this manufacturing facility, in contrast, an industrial system is used. In such a system, the flow rate through the collector is reduced when the air exiting the collector is below the minimum desired temperature. This does two things. First, with a lower flow rate, air resides in the collector longer and is therefore heated to a higher temperature. Second, the difference between the design air flow rate and the reduced collector flow rate is made up by inside air drawn from near the ceiling and mixed with the solar air. This reduction in the collector flow rate is such that the temperature of the mixed air attains the desired minimum. The indoor air temperature is 21 degrees. The minimum air temperature is 15. This building has high internal heat gains and tends to overheat, so it is okay if we bring in cooler air and mix it with the warm air at ceiling level. For the maximum air temperature, I'll enter 20 degrees Celsius, indicating that we don't need air at a temperature above 20. This building already overheats, so heating above 20 degrees will not be considered a benefit by RETScreen. For the indoor temperature building stratification, this parameter indicates how much hotter the building inside air is at ceiling level, where hot air accumulates, versus floor level, where occupants are. With high ceilings and equipment acting as point sources of heat, you would expect a high level of stratification, that is, a much higher ceiling level temperature. But in the actual fact, this was measured and a difference of only 1 degree Celsius was found. I'll enter 1 degree, therefore, for the building stratification. The floor area is 116,000 square meters. The R value of the roof is 1.5. Note that that is in metric units. The R value of the wall is 1, also in metric units. If you want to see this in US customary units, you can use the unit switch. So it's not a very well insulated building. I'll fill out the next sections for the base case only, and then, since the parameters are identical in the proposed case, I'll use copy base to proposed to repeat the same parameters for the proposed case. The design airflow rate is 1 million cubic meters per hour. The building operates 24 hours a day, 7 days a week. We have a southeast and a southwest facing vertical wall where we can install the solar collectors. The slope will therefore be 90 degrees. For the azimuth, RET screen does not differentiate between east and west, so southeast and southwest are both 45 degrees. I can consider this to be a single wall with an azimuth of 45 degrees, therefore. Clicking on Show Data reveals a table with monthly usage of the system. We know that heating is not required from mid-May through mid-September, so to ensure that RET screen does not accord any benefit to the solar air heating system during these months, for the percentage of the month the system is used, I'll enter 50% for May and September, 0 for the summer months, and 100% for the other months. Now I'll use copy base to propose to fill out the proposed case with the same parameters for the monthly percentages and the earlier section with the design airflow rate and the operating hours per day. I'm going to look at using a transpired plate collector. That is a perforated unglazed metal plate with outside air being drawn through the perforations to a plenum behind the plate so as to reduce the heat losses by gusts of wind or convective currents. The design objective is used to size the collector. For each of the choices of objective, there is a target airflow rate for each square meter of collector. Knowing this, as well as the design airflow rate for the entire system, RET screen can determine how big the collector needs to be to meet the objective. I am in the situation, however, where I know that I have 8,826 square meters of space available for the collector, and I want to see if that is a reasonable size for the collector. I'll set the design objective to standard operation for now, and revisit this once I've entered the collector area. I could visit the product database to look for a particular solar air heating technology, but here I will just specify that the solar collector color is a dark gray that achieves a solar collector absorptivity of 0.85 or 85%, indicating that 85% of the sun's incoming rays are absorbed by the collector. Black would achieve a slightly higher absorptivity, but was not chosen for aesthetic reasons. The performance factor is a parameter that indicates how well the particular solar air heating technology chosen functions compared to a standard design. A value of 1, which I will use here, indicates that the chosen technology performs exactly as a standard design. In Help, you can read about standards that are used to evaluate the performance factor for real-world products. We can now compare the available wall area of 8,826 square meters with the sizing proposed using the design objectives. With standard operation, we'll need a bigger collector, and with high air volume, a smaller collector. So the use of all 8,826 square meters for the collector falls between the two and is acceptable. The system will have relatively high flow rates through the collector, which will result in low temperature rise but relatively efficient operation. We'll assume that buildings around this plant cause some shading of the solar collector during winter. I'll specify a 10% reduction in solar energy reaching the collector for the period of mid-September to mid-May. Winds influence the performance of the collector. Higher winds cause higher convective heat losses and thus less efficient operation. Our estimate of the wind speed found on the facility page is taken at 10 meters height. This is higher than most of the area of the wall, and wind speeds tend to be lower near ground level. Also, surrounding buildings will block wind from certain directions. As a first guess, we'll assume that the wind speeds are 30% lower than as measured at the Dorval Airport at 10 meters. In order to draw 1 million cubic meters per hour of air into the building, we'll need a fan that will consume electric power. Note, however, that we'll need a fan even if a solar air heating collector is not used. So the question is really, will the fan consume more power simply due to the presence of the solar collector? One argument could be that the pressure drop across the perforated collector will be slightly higher than for an open vent, suggesting slightly higher electricity consumption. Countering this, however, will be the buoyancy of the solar heated air, which will want to rise up the plenum and drive itself into the distribution system. In practice, these may cancel, resulting in essentially no difference in the fan power requirement from the base case to the proposed case. Therefore, we'll enter 0 here, reflecting that we expect this to be the case for this building. I have a quotation for the cost of purchasing and installing the system. It's $343,824. This is a fairly low cost, but keep in mind this is a very large collector, so there are economies of scale. And furthermore, for this building, the exterior cladding needed to be replaced in any case, so only the additional cost of a solar air heating collector versus standard cladding needed to be considered. For operation and maintenance costs, I'll enter 0. There is no additional maintenance for this unglazed perforated metal plate compared with a standard metal exterior cladding. Fan maintenance would be required regardless of whether there's a solar air heating system implemented. In the summary section, we see the results of this analysis. There is no requirement for additional electricity for the fan, as we discussed earlier. The heating delivered cell indicates the savings from the sun's heating itself. It delivers 1.8 gigawatt hours of heat per year, reducing natural gas consumption. In addition, there are savings due to building heat loss recapture and destratification. The building heat loss recapture refers to losses from the walls on which the solar collector is mounted. These are reduced by around 1 gigawatt hour per year. About half of the heat that is migrating from the inside of the building outward through the wall is captured by the air in the plenum and re-enters the building, so that's a savings. For destratification, this results in savings of 1.8 gigawatt hours per year. That is a figure almost exactly equal to the heating being delivered due to the sun's heat itself. By reducing the temperature of the ceiling air, heat losses through the roof are reduced, and the system makes use of the overheated ceiling air to heat cool ventilation air that's brought in and distributed at ceiling level. Clicking on the down arrow beside other information shows some additional information about the operation of the collector itself. The first line, the solar collector fan flow rate, indicates that the sizing of the collector versus the desired design airflow rate results in a nominal or design airflow rate of 113 cubic meters per hour for every square meter of collector. However, as discussed earlier, this rate is reduced when exterior temperatures are cold in order to achieve, with the mix of interior air, the desired minimum air temperature. Taking into account this modulation of the flow rate through the collector, the average annual value for the solar collector flow rate is 59 cubic meters per hour per square meter of collector. On average over the entire season of use, there's a 5.2 degrees Celsius air temperature rise for the solar heated air, and this results in an efficiency of 16.2%, which seems a bit low, but keep in mind that that is being calculated, as indicated on the help, by comparison with the total solar energy available over the entire year. And much of that is available in the summer when we don't have use for heating, so it makes the efficiency look lower than the actual operational efficiency during winter. For the heating system, for both the base case and the proposed case, we will continue to use the air heating system that we defined earlier. That's the natural gas 75% efficient system. In the base case, we require 40.4 gigawatt hours of heat per year. In the proposed case, the solar air heating system reduces this to 35.7 gigawatt hours per year. So a reduction in the thermal requirement from the natural gas-fired system is only 11.6%. However, we are saving 4.7 gigawatt hours per year, which is a lot of savings. And this is reflected on the include measure table, where we see that we have fuel cost savings of $118,000 per year, which results in a simple payback of just under 3 years. Going to the finance page, for the parameters that are by default used here, we see that we have a very profitable project.